So what we're going to talk about today are titrations. And essentially we need to know what a titration is for, and what it's for is to determine the amount of an acid or base in solution that we don't know the concentration of. And the way we do that is by adding in something that we know a concentration of. So if you see over here, this right here would be the concentration that we know and the thing that we know, and we pour it into the thing down below here that we don't know about. So we call the thing that we're adding in, we call that the titrant, and the thing that we are trying to figure out the concentration of, we call that the analyte. So essentially what we do is this is a burette, and we fill it up with a certain amount of known concentration, and we drop it down into here until we use up all of the analyte. And when we get to that point, we call that an equivalence point or a stoichiometric point, which we'll talk about in a little bit. And the way we usually track this is via a graph. Now, there are three different types of titrations that we're going to focus on. There's actually four that we're not going to focus on right now. One's called an oxidation reduction, so wipe that from your brain. We're not going to deal with that. But we have a strong acid, strong base, a weak acid, strong base, and a weak base, strong acid. So of the different permutations, the one that we're not going to be working on is is the weak acid, weak base titration, because that would be a nightmare mathematically. So we are going to jump into actually doing a titration, or showing you how to do a titration with a strong acid and a strong base. Before we do that, let me go back to what molarity is. So let me remind you that molarity is moles per liter, and it comes in the unit, the molal, or capital M. Now, since that is in moles per liter, that means that we have to deal with volumes in terms of liters. And when we're dealing with burettes, those typically come in milliliters. So what we do is we divide both these by 1,000, and we typically do a lot of our calculations, and whenever we're dealing with moles, instead of moles, we deal with millimoles. And that's essentially 1,000th of a mole. That's what milli means. And instead of dealing with liters, we deal with milliliters. Now, if you do the mathematics here and you compare a mole, so over here, mole to a millimole and a liter to a milliliter, they are exactly 1,000 times smaller. So this times 1,000 gets us to moles per liter. And since they're both equivalently 1,000 times smaller, what we're going to do a lot of is in all of our calculations where we're using equations or whatnot, we're going to use the millimole. And whenever we're dealing with volumes, we're going to deal with milliliters, because ultimately when we deal with molarity from here on out, we can do millimoles per milliliter. And if you do the math here, you could just cancel out milli, and do you see how the ratio stays the same? So we're going to be, that's just a heads up, because whenever we're doing problems, you're going to see that they're going to deal a lot of problems with these smaller units. So let's jump straight into a titration case. And the titration case we're going to deal with is a strong acid with a strong base. If you notice here, we have a graph, and on the bottom of the graph, we have the amount of NaOHs being added in milliliters, and then we have the pH going up the graph. Now, they start us off in a problem. They give us 50 milliliters of HNO3, and that's what's being titrated, and we're titrating it with 0.100 molar NaOH. So what we want to do is we want to see what is the pH when we just add stuff in to our HNO3. But first we're going to try it where we have 50 milliliters of the HNO3, and we want to know what is the pH of that. Right? Now, the thing that's missing on this one that I probably should have written in here, it's actually 0.200 molar, because if you don't know the molarity, you're kind of stuck. So we have 50 milliliters of 0.200 molar HNO3. And before we add any NaOH into this, wouldn't you agree with me that all we have is 0.200 molar HNO3? And if that's the case, can't we draw this correlation? If we know the HNO3 concentration is 0.200 molar, wouldn't that mean, therefore, that the H plus concentration is 0.200 molar? And if we wanted to take the pH, wouldn't that be the same as taking the negative log of the H plus concentration? And not to spoil the tremendous surprise here for you, but if we do the math on that, the pH is going to be equal to 0.699. And we've plotted that on the graph over here. You can see that is our starting point. Now, what we're going to do is we're going to continuously add different amounts of NaOH to our HNO3. And one of the things that you need to be aware of is this is what we're actually doing up here. I'm going to put at the top of my notes here. We have HNO3, and we're adding NaOH to it. But There are some spectators here. So what's really happening, this and this are doing nothing. So our net reaction is we're adding H plus to OH minus, and it's forming H2O. So whenever we deal with any sort of titration problem, we're first going to take care of the stoichiometry, dealing with getting rid of whatever we're dropping in. So in this particular first case right here, we're gonna start off with, if we look at our H plus concentration, if you take a look, we have 50 milliliters of 0.2 molar HNO3. So if I were to take a look at that, 50 milliliters of 0.200 molar HNO3, if I rearrange the molarity equation, which is molarity equals moles per volume, and I rearrange that, wouldn't molarity times volume be equal to moles? So if I do that, I can then rearrange this equation and realize that if I multiply this out, 50 milliliters by, actually that should go here, right? And this should go here, 0.200 molar. What that means is I'm gonna get 10.0 millimoles as my number of moles of HNO3. So when we do our adding of our two things together, my H plus and my OH minus together to get H2O, which is a neutral solution, if I start off with H plus, I know that I have 10 millimoles of H plus initially, 10.0 millimoles. This is before we do anything. And I'm gonna add in 10 milliliters of 0.1. Now, if you do the math, and again, this is my volume and this is my molarity, and if I multiply those two together, will I not get my moles? And if I do that, I would end up with 1.00 millimoles of my OH minus. So after the reaction's done, and remember, this is a 1-to-1 ratio, would you agree with me that the change is gonna be, I'm gonna lose, since this is a 1-to-1, I'm gonna lose 1.00 millimoles of this, and I'm gonna lose 1.00 millimoles of this. And the end result will be, at the end, I have 10.0 millimoles of the H plus, and I'll have none of this. We don't care about water because it's a liquid. So I don't know why I wrote 10 again. That should be 9.00. So what I have now is I have 9.00 millimoles of H plus sitting in there after I've added in the 10 milliliters of 0.1 molar NaOH, which is the same as 1.0 moles of NaOH or OH minus. I want to figure out what the pH is of this, and in order to do that, all I have to do is I have to then divide that into the new volume. Now, be really careful here, because originally DCI had 50 milliliters of the HNO3, and I've added in 10 milliliters. So my new volume, so if I do my molarity equation, isn't it going to be my moles or my N per V, right? So I'm gonna have to add both my 50 milliliters that I had originally of my acid to the 10 milliliters of NaOH that I've added in. That's going to give me my H plus concentration. And when I do the math on that, my H plus concentration is gonna equal 0.15 molar. Now, if you're wondering how I did that, I literally just took my moles and my millimoles, sorry, and I divided by my 60 milliliters, and I got 0.15 molar. That is my H plus concentration. And if I took the negative log of that, of the H plus, because that is what pH is equal to, I would end up with 0.82 as my pH. And if you take a look here, very slight increase here. See how my B is very slightly above it after I've added in 10 milliliters. So let's keep on adding in different amounts of the base that is titrating. Now, I want you to take a look at this when we put this in here to begin with here. Are you okay with understanding that if I add in 20.0 milliliters of the NaOH, if I multiply that by 0.100 molar, since molarity times volume is equal to moles, couldn't I get the number of moles I have? Wouldn't that be 2 millimoles? And in the back of our heads, we need to realize that we started off with 50 milliliters of 0.200 molar HNO3, and if we multiply that out, that is 10 millimoles. So for every one of these problems, our starting point in our little container down below is we have 10 millimoles of the HNO3, and we're dropping into it via the pipette or via the burette different quantities. So in this case, we're dropping in 2 millimoles of this. So when we set up our mathematics here, it's going to be very similar to what we did before. We're going to have H plus, and we're adding in OH minus to it, and it's going to form water. It's going to neutralize. So if that's the case, we're going to initially have, before the reaction, we're going to have 10 millimoles of this. I'm being very kind of loose with the significant figures. Here I'm going to have 2 millimoles of this, and we don't care anything about that because we're ugly that way. And after we're done, since this is a 1-to-1 ratio, won't the 2 millimoles get completely used up? And then won't 2 millimoles of this react with 10 of this to give us 8 millimoles of this? So again, when we're done, we're going to have none of the OH minus in here, and all we'll have left over in our container down below here is going to be 8 millimoles of the H plus. But since we added in an additional 20 milliliters to the 50 milliliters we have here, our volume at the end is going to be 70. So if we take a look at our molarity is going to be our millimoles, 8 millimoles, divided by our 50 milliliters plus 20 milliliters, and that's going to be equivalent to 8 divided by 70. Again, a horrible lack of care for significant figures. I think that it should be something like this: milliliters and millimoles, and these two things cancel out. And when I do that, I'm going to end up with a concentration for my, let me see if I can track where I've done the math here already. I'm going to end up with an H plus concentration of 0.11 molar. And if I take the negative log of that, I'm going to end up with a pH of 0.942. Now, again, you can take a look here, and if you were to divide this up into numbers, which I'm very bad at, 1, 2, 3, 4, 5, 6, this here is just below, the C mark is just below 1. I'm not going to do the same exact, repeat the exact same math here, but what we're going to do for this is exactly the same as this, except for, if you take a look, we're adding in 5.00 millimoles of NaOH versus the 2 millimoles of NaOH that we added up here, right? And if we do that, we discover that at point D, which is right here, point D, our pH is equal to 1.301. So that's this spot right over here. Now, the formatting got a little bit wonky here, but what if we added 10 millimoles of the NaOH? Isn't that what 100 times 0.1 is? I'm going to do the work up here just so you can see it a little bit better. So this is a very special point in our problem, because wouldn't you acknowledge that we said from the beginning, when we look at our H plus, we have 10 millimoles, 10.0 millimoles of that to start with. That's the HNO3, we don't care about the NO3 minus, that's the 50 milliliters of 0.2 molar, we get 10 millimoles of this. And now when we add in 100 milliliters of 0.1, that's the same thing as getting 10 millimoles of NaOH. So now we're adding in 10.0 millimoles of the OH minus. This is actually a pretty pivotal spot, because if you look right now, if they go in a 1-to-1 relationship, won't we have 0 of this and 0 of this? And whenever we've used up our original amount, that's a special place called the equivalence point. It's also known as the stoichiometric point. These are words that I do not like having to print out like this, but the net result is we have no H plus and we have no H minus, and if we have none of either of them, all we have is just H2O, which is neutral, and neutral, isn't that a pH of 7? So that's why we see right here our equivalence point, this is our equivalence point, is exactly at 7. Now, I should be really clear. The only time that at the equivalence point we have a pH of 7 is when we have a strong acid and a strong base titrating each other. Either direction, it always works the same way. We'll always have a pH of 7. But that's only when we're dealing with a strong and a strong. When I show you how to do titrations where we have a strong and a weak, that will not hold true. So let's move on and let's kind of finish this off here. What if I added now 150 times 0.1? I hope you guys are seeing the math in my head here. That's 15 millimoles of OH minus. Each time, by the way, we're not adding in an additional 15 millimoles to the amount we already had. We're pretending we're starting from scratch again, and we have in our container, we have 10 millimoles of our H plus, which is really HNO3, right? And to that, we're now adding 15 millimoles. It's each time we're starting from the beginning and seeing what we'd end up with. So again, we're going to write our equation out. H plus OH minus goes to H2O. And in this case, we have 10 millimoles of this. We have 15 millimoles of this. And when all is said and done, we have our start and we have our finish. And if I was keeping sequence, I was calling it before and after. But wouldn't we have none of this left? Because 10 millimoles of this, won't it work out? We lose 10 millimoles of this, and won't it take 10 millimoles of this with it? And then at the end, won't we end up with 5 millimoles of OH minus? And here's the thing. Now for the first time, we have leftover OH minus. Now here's what's important. We can still find the pH of this out, but see how I have 5 millimoles of OH minus? Well, if we want to figure out the molarity, isn't molarity always moles per volume or millimoles per milliliter? Well, we know our millimoles are now 5 millimoles of OH minus, and we know that we have 150 milliliters, because that's what we're adding in, to the original 50 milliliters that we had at the very beginning. So that means altogether down below we have 200 milliliters. So if we divide that out, my molarity is going to be 5 divided by 200. And we do the 5 divided by 200, we're going to end up with 0.025 molar. And if you were to take the negative log of that, we would end up with a number that I don't have right now. What they did in the textbook is they actually did this. They said, well, if we know our H plus, or we know our OH minus, we can figure our H plus, because it's 1.0 times 10 to the negative 14 is equal to H plus times OH minus. So if we know this is 0.025, right? And we know this is 1.0 times 10 to the negative 14, we can isolate H plus. And when they did that, they got the H plus value of 4.0 times 10 to the negative 13. I would have preferred, and I just don't want to, I don't have my calculator here with me right now, of course. I would have just said, if we know that this is equal to my H plus my OH minus concentration, couldn't I go negative log of my OH minus? Isn't that equal to my POH? And then couldn't I go 14 subtract POH equals my pH? Either way, if you do it, you end up with a pH equal to 12.40. And that's this markup here. Now, typically what they do is they do one final point that's just so far gone that it's not even really a reasonable point to deal with. And in that case right here, we deal with something like this. And the graphs got a little bit backwards, but do you see how in this case, they did 20 millimoles of the OH minus. And if you take a look, I don't know if we can do this simultaneously. If you take 20 millimoles of this, you're gonna see that the pH kind of evens out after a while, right? So the pH, if you did 20 millimoles, you'd end up with a pH of, I want to say, is 12.60. So it's 12.60, and this was originally 12.40. So on this graph right here, if you take a look at it, this is 12.40, this is 12.60. Now, how do we actually make a graph? Because you aren't doing a connect the dots. We actually do a kind of a fluid thing. Now, do you see how the graph here, it kind of goes straight, and then all of a sudden it shoots up, and then it goes over? This is typical of every type of titration. Now, if I were doing connecting the dots here, I would go straight until I got almost to the E mark, and I'd shoot up until I get almost to the end, and then I'd even out. And that is your typical titration curve. Now, the exact opposite occurs when we're titrating a base. See how we start off at 14 and we go kind of on a very slow angle until we get close to the equivalence point, and then we shoot up, and by that I mean shoot down and then even up. These two graphs are opposite of each other. So what we're going to be working on after this is we're going to be working on weak acids and weak bases being titrated with opposite strong and strong acids and bases. I would suggest looking in your textbook to example that we can find on page 728 if you're looking at it, or the sample examples would be 14 or 15.4 is the section you'll be on. Hopefully this has been helpful. There are notes that you can look at online that will allow you to draw these graphs along with. I hope this helps. Thanks. Bye.